Hello everyone, and welcome to today's lecture on FPGA design with Verilog. In this lecture we're going to be covering sequential logic. I've decided to rename this series to FPGA design since it kind of makes a little bit more sense based on where I want to take these videos. So in this lecture we're going to be talking about procedural assignments, conditional programming constructs, team system tasks, and test benches. Procedural blocks. Procedural blocks are sections of code that execute procedural statements like assignments, if, case, loops, etc. There are two kinds. Initial blocks run once at the start of simulation. Always blocks run repeatedly, driven by events in their sensitivity list. Both are concurrent. Multiple procedural blocks execute in parallel during simulation. The initial block. The initial block executes only once, starting at simulation time 0. It is used mainly in test benches, so it's not synthesizable, and is often used for initialization or stimulus generation. So the basic outline would be initial begin, some statements, and then end. So example, in module TB initial example, we declare some registers A, B, and then initial begin, A is equal to 0, B is equal to 1. And after 10 time steps, A is equal 1. After another 10 time steps, B is equal 1, and after another 10 time steps, we finish. The always block. The always block executes continuously whenever triggered by whenever it's triggered by its sensitivity list. It is used for combinational or sequential logic. So this would be the basic outline of an always block. So with your sensitivity list, begin, and then your statements. So in combinational logic, you would make sure that you're sensitive to all signals. This ensures the block reacts to any input change automatically. In sequential logic, you would usually usually triggered by clock edges. Sensitivity list. The sensitivity list tells Verilog when to re-execute the always blocks. There are two kinds: event-driven by signal changes, and edge-driven, triggered by clock edges. Always at A or B or C, so whenever these signals change, Y equals A and B and C. And always at positive clock or negative edge reset, which is edge-driven. So positive edge means positive rising edge, and neg edge means negative or falling edge. Some examples. So for some combinational logic where we want to model a mux, we would declare a module with a output register Y, input wires A, B in selection, and always at any time any one of these signals change, and then begin. If cell is true, Y equals B, else Y equals A. In sequential logic, for our D flip-flop module diff, we declare an output register Q, and input wire D, clock, and reset. So always at the positive edge or the negative edge of reset. If not reset, Q is equal to 0, else Q is equal to D. Blocking versus non-blocking assignments. So this is very, very important. We use blocking assignments to execute immediately. It is used in combinational logic for the equals. In non-blocking, we arrow equals, which executes in parallel, using sequential logic. So here's a combinational example, and here's a sequential example. Multiple procedural blocks. You can have many initial and always blocks in a module. They'll all run concurrently. Module concurrent example, register clock equals 0, always number 5, clock, after 5 time steps, the clock will go up and down. Initial begin, at time step 100, will stop after 100 time units. Statement groups. A statement group in Verilog is a set of one or more procedural statements that are treated as a single unit. Statement groups are used inside procedural blocks such as initial, always, task, and function. You can use statement groups to control execution order and scope of variables. There are two main types: sequential block, begin and end, and parallel block, fork and join. For a sequential block statements execute in order. one after another sequentially. They are commonly used in both simulation and stimulus, and are often used inside always or initial blocks. So begin statement 1, 2, and 3, and then end. And then, for example, always at star, or so any signal changes begin. Sum is equal to A plus A or B, and carry is equal to A and B. Parallel block. Parallel block statements run concurrently in parallel. They are used mainly in test benches and not are synthesizable. The block units. Alright, so parallel block. Parallel block statements run concurrently in parallel. They are used mainly in test benches and are not synthesizable. The block waits until all parallel statements finish before continuing. So fork and join. So example, initial fork executes after 10 time units, 20 units, and 30 units, A, B, and C. Local variables. A local variable is a variable that is declared inside a procedural block or statement group, such as an initial, always, task, or function. It only exists within that block and cannot be accessed from outside. In short, local variables are private to the block. Their lifetime is limited to the execution of that block. They are initialized when the block starts and discarded when it finishes. Example, a module sum example, output register of an array of sum, input wire AB. Always at any time something changes, we declare it a temporary variable. Set temp equal to A plus B, and then sum equal to temp. Okay, if-else statements. If-else statements are used for decision making. They evaluate a logical condition. They execute one block if true and another if false. So if condition, we execute statement 1, else statement 2. For example, at 2 to 1 mux, always after any change in the input signals. If cell is 1 or true, y is equal to b, else y is equal to a. Case statements. Case statements are used for multi-way selection. They are similar to a switch statement in C. They compare an expression to a list of possible values. So for a case, this has how it would be outlined. Case expression, value 1, statement 1, value 2, statement 2, and we have a default. So for example, for 4 to 1 mux, anytime an input changes, in the case of selection, if 0, y equals a, if 1, y equals b, if 2, y equals c, and if 3, y equals d. And default, we don't care. Loops. So here are examples of some loops. We have our forever loop. It is not synthesizable. So for every time, every 5 seconds or time steps, the clock goes up or down. And then this is a while loop. So while I is less than 5, we will loop. And then a repeat loop. So we repeat a fixed number of times. And then a for loop. So their initial condition, I is equal to 0, as long as I is less than 8, and we increment I after every loop or iteration. Disable. Used to prematurely terminate a name block, a fork join thread, or a looping construct. So we can disable the block name. For example, initial begin with a name of test block. We declare an integer I, we begin our for loop, and if I is equal to 5, then we disable the test block. A loop. So putting it all together with all the loops, we declare a test bench called control flow. We declare a clock, a count register, and an integer I. So we forever loop the clock. And then here is our main test process called test process. We set the count equal to 0. We repeat for 10 cycles, and at the positive edge of the clock, we increment count. And if count is equal to 5, we display halfway there. If the count is equal to 10, we display done at time t. And then we exit early using disable if count is equal to 8. System tasks. In Verilog, systems tasks are built-in commands that start with a $sign and are executed only during simulation. They are not synthesizable. They are essential for displaying text, reading and writing files, and controlling and monitoring simulation behavior. So we have 4 categories: text output, which prints or formats data to a console or file; file I/O, to read and write external files; simulation control, to control simulation execution; and simulation monitoring, to track or dump signal activity. And these are the examples of the keywords we would use for each category, which I'll display in a little, and which I'll explain in a little bit. So text output system tasks. Display prints text and variable values once to the console and automatically adds a new line to the end. So we display A, B, and sum, and we print out A is equal to 0, B is equal to 1, and sum is equal to 1 for, whatever the variable variables happen to be. Same as for write, same as display, but does not add a new line automatically. Monitor continuously prints whenever a listed variable changes. So whenever one of these variables changes, we automatically update the monitor. And strobe is similar to display, but prints after all non-blocking statements are evaluated in the current time step. File input-output system tasks. So for file open and close, we open a file and return a file descriptor, and fclose closes it. So an example, we declare an integer called fd. We begin. So we set fd equal to file open. We open the file results.text for write mode, and then we write the simulation results into the file, and then finally we close it. So fdisplay, fwrite, and fstrobe are similar to display, write, and strobe, but send output to a file instead of the console. The scan function reads formatted data from a file, so we would declare an integer of fd, r, a, and b, and then begin. We open the file for reading, and then we set r equal to the scan the result of the scan function. We look for the integers a and b, and then we display in the console what the integers are, and then we close the file. And finally, a special case, we read memb and read memh is used to initialize memory from a text file. So you would use read memb for binary and read memh for hex. Simulation control and times tasks. So stop, self-explanatory, it just pauses the simulation. Finish ends the simulation, and time just displays the current simulation time. And these are the different times, so 64-bit, 32-bit, and a real or floating time. Simulation monitoring and waveform dumping. This system tasks allows you to record signal activity for waveform viewers like GTK Wave or ModelSim. Initial begin, so we dump the results into a wave.vcd, and then dump vars 0, into testbench, record all signals in testbench. So we generate a value change dump file for waveform viewing, and is common in all simulation workflows. So putting it all together. So we write a test bench called system tasks. We declare a register AB, a wire sum, an integer for FD. We declare a device under test called adder. So input A, input B, and output sum. Initial begin, we set up the file. So we open the file output.log for writing, and then we write time A, B, sum in it, and then we begin our simulation loop. And after 10 time units, we display whatever the A, B, and sum happens to be. And then we write A, B, and sum into the file. We end the simulation by closing the file and finishing the simulation. Finally, we declare a dump file called adder.vcd, and we dump the variables into, at the beginning of the file, the results of TB system tasks. Test benches. So, a test bench is a Verilog module used only for simulation. It provides input stimulus, signals that drive the device under test, output observation, printing, monitoring, and waveform dumping, and automatic checking of results. Test benches are not synthesizable. They do not describe hardware. They exist purely to test and verify the logic design. So we declare a simple test bench where we would declare some test bench signals. Initiate the device under test. So we would call a module called mux2to1, call it the unit under test. We put our registers into it. And then finally we generate some stimulus. So after some time steps we just change A, B, or cell, and then we finish. And then finally we monitor and print. So we're going to print any time A, B, or cell or Y changes. Common stimulus generation techniques. So we can use initial blocks, always blocks, loops, including for, repeat, and forever. Automatic result checking or self-checking. So we write this test bench called mux check. We declare some registers, a wire, and an integer called errors set equal to 0. We use the module mux2one and call it the unit under test. We send our variables into the module, then we begin. So we do a for loop, and we set A, B, and cell equal to 0. Wait for signal propagation. If y is not equal to if y not is equal to cell, if B or then else A, then begin. And then we display an error at time whatever it was, and then errors is equal to errors plus 1. So if we encounter any errors, we'll say test failed with 0 with how many errors, and then else if we didn't get any errors, test pass. So using external files and test benches, read input stimulus. Alright, so we read the input stimulus, so we declare some registers called A, B, we declare an integer called FD. So we open a file called input.text, and while we have not reached the end of file, we scan for A and B, and then we display A and B. We close the file. We write the simulation results, so we declare an integer called outFile, initial begin. We open a file called results.log for writing. We write time A, B, Y, and then we write A, B, Y into the file. So putting it all together. So we declare a test bench called adder. Then we declare a register A and B, a wire sum, an integer I, an output file. We use a module called adder4. Name it device under test. We put our variables into the module, initial begin. So we open a file called adder results.log for writing. We write into the file time A, B, sum, and expected. Then we go into a for loop where we set A equal to I and B equal to 15 minus I. Then we write into the out file the current values of the time, the A, B, and sum. And then finally, if sum is not equal to A or B, then we display error. And then we close the output file, and then we finish the test. Alright, so that concludes this lecture. Thank you very much for watching.